Welcome everyone to our presentation today called Enter Sandbox. Before we start with the content of our presentation, let us briefly introduce ourselves. My name is Claudio Canella. I'm a PhD candidate at Graz University of Technology. If you ever want to reach out to me, ask some questions, feel free to do so on Twitter or simply send me an email.
Hi, so my name is Mario Werner. I was a PhD at Graz University of Technology as well when conducting this research, and now I'm a hardware design engineer at NXP Semiconductors. So if you want to reach me, have a look at my homepage and you find the contact information there.
Hi, my name is Michael Schwarz. I'm a faculty at CISPA Helmholtz Center for Information Security. Also, if you have some questions, feel free to always reach out to me on Twitter, via mail, or ask questions after our talk. So what is this talk about? We already know that memory safety vulnerabilities, they are quite common. So everything is quite buggy. We have vulnerabilities everywhere. And there's this nice technique of sandboxing that helps in limiting the impact of vulnerabilities. That's something that we really want to use in all these applications that could have bugs and are a target for exploitation, like browsers, for example. And if you're on Linux, there's already a nice technique, the seccomp filters, and they allow us to sandbox an application so that they only have limited access to system calls. But this is still something we'd have to do manually. So the question is, can we automate it? Can we get sandboxing in more applications than we have right now?
A few months ago.
So I was coding a little application. I needed a small application to copy some files around. And I wrote that in my favorite language, in C. Of course, I know if I write applications in memory unsafe languages like C, it's easy to make some mistakes, to introduce bugs, maybe even exploitable bugs. And that this is quite common, we can see that here, for example, in this plot. So I looked at all these CVEs regarding memory safety, vulnerabilities, things that were exploited in native applications. And we see we have quite a lot of them. And these are only the known ones that received an identifier. I don't want to make this graph any steeper, so I'd like to not have any vulnerabilities in my code.
So Michael, your application sounds to be perfect for seccomp. So let me briefly introduce what seccomp is. With seccomp, we have this application, like for instance, in your case, your application for copying files, and typically it just wants to perform some system calls to perform its task. So you identify the system calls that your application does or does need, and it installs the filters in the kernel. So it just says, if you get an open system call, please allow it. So we get the system call, then after the filters have been installed, the application performs, for instance, this open system call. The operating system, the Linux kernel, checks within the filters if the system call is allowed. If it is not, it is simply going to terminate your application because it might have been exploited in some way or form. And if it's allowed, then simply we allow it, or the system call is executed, and we return.
That indeed sounds fascinating. So from the basic idea, I get it. But are you serious, Claudio? So I looked at that. So you explained it so nicely, and I thought like that's a plug-in solution. I just put it into my application. But then I found some tutorials and it looks like that. So that looks nothing like C code or anything I know. That looks more like some type of pseudo assembly stitched together using C macros. And it's horrible to read and even worse to write that. So I don't know. So it sounds cool, but I have no idea how I should come up with things like that. I mean, it might work for a simple Hello World application, but for anything larger, I don't know.
Well, yes, that's because you use the BPF filters directly. The filters are expressed in this language called BPF, and it's really complicated. But why not just use libseccomp? It's more or less an API. It does everything for you in the background, and it's really nice. You have these functions, you just create a context, you call seccomp rule add with the number of the system call or the name of the system call that you want to perform, and it's done. So why not just use that? It's a lot more easier.
Okay, that indeed sounds a bit more practical. So I looked that up. I looked at libseccomp, and yes, you are kind of right. So it definitely looks easier than what I tried to do before. That's now actual C code with some functions. But still, it doesn't look very nice and it looks super complicated, and I had to look up many things in there. So we have something like the RT sig return or exit group, open add. Like, why did I need all of that? I mean, I don't really know, but if I didn't add that, it crashed. So it must be necessary. And after a bit of research, I figured out like these are the syscalls that are internally used by the code, by the C code. And I have to figure out which syscalls my application uses. But how would I know that as a simple developer? So I have C functions. How can I map them to the syscalls that they actually use? And I would have to do that for the entire code base. So again, for Hello World, that's fine. But if I have a large application with thousands of lines of codes and multiple files, doing that for all the C functions, checking which syscall they use, does that really sound feasible to you? I don't know, it doesn't to me. And then again, typically I use some third-party libraries and they have a lot of code again. So I would also have to do that for all the third-party libraries? Really?
You're right. We need to do something about that. So maybe we can come up with a solution for that.
Months of research and engineering later.
We came up with this solution that we call Chestnut. And Chestnut is more or less a two-phase approach. So in the first phase, we have this, we call it P1, we have the static analysis. And it's more or less what you said. We take the source code of an application, we use our tool that we call Sourcealyzer, it performs some analysis, and at the end, it tells us what are the system calls that the application is going to execute. And in the other case, maybe we don't have the source code available, and we only have the binary, so we also have a solution for that. We use our binary, we use our tool called Binalyzer, and we again get these annotated files. But this might not work entirely because static analysis does have its problems. So we have this optional second phase called the dynamic refinement phase, where we have a third part of our tool called Finalizer. And with this dynamic analyzer, we can simply do some runtime tracing of system calls, and we can refine the system calls that we find. And we get, again, these annotated binary files that we can then use another tool called either Chestnut Patcher to generate a Sandbox binary or Chestnut Generator that generates us a wrapped binary. But that's a lot of information for just this one slide. So maybe let's take a closer look at all of these components individually. Let's start with the first part, Sourcealyzer. As I said, we have these source files, like for instance, you're copying files code. We simply pass it through our extended compiler. We extract the system call number there. Then we need to build up some call graph. We need to know which function calls which so that we can extract the correct system calls in the final binary. After this, we take the object file that we have, we annotate it with the call graph that we found and the system calls that we found within this single file. Then we combine it in the linker with the additional libraries that we have. And we flatten this call graph. We get the system call numbers out there for the whole binary that we actually need. And we generate this annotated executable. And once we run it, we're simply going to install the filters. Sounds nice, right? You just need to use our extended compiler that we provide, and your application is sandboxed.
Do you even know how challenging it is in practice? I mean, you make it sound really simple.
No, I don't know.
Okay, so let me show you how this all works with the help of one example. So we take the most important program in computer science. Everyone knows it, Hello World. And the challenge or that we have, what we want to achieve is we want to sandbox this application. And you nicely explained, we put it into the compiler and he does all the work and we're done. But if we really try it and look at what the compiler actually sees, it's not that simple. Because when you compile this program, everything the compiler sees is a call to a function called putString. The compiler has no idea what this function is, where it has been defined, what it does internally, and he doesn't care. He only looks at one translation unit at a time. So we can manually look up this putString function. We find it in our C library implementation, looks something like that. On the first glance, it's still really complicated. We see some function calls, some macros there. And when we let the compiler do its work, we see internally putString calls for other functions. But again, nobody knows what these functions do. And the compiler doesn't care. So one thing which we do in our tool in Sourcealyzer is that we extract all this local information. Each translation unit only knows about the code it contains and what other functions it calls. And what we do here is we serialize this information. In this case, we simply pick JSON and we embed this JSON into a node in the resulting object file. So we can use the elf nodes there and just add arbitrary information. In the second step, the linker, which has the task of combining all these object files, loads also this new added node sections and uses this information fragments to recombine all this information and construct a control flow graph, or in this case, a call graph. So when you look at the slides here, we see main calls putString, putString calls for other functions. The one which is important is fputString. If we follow this path further, we find that this internally calls fwrite, and fwrite again calls a few other functions, but we still have no idea where the actual syscalls are. We haven't seen them here. The challenge is that fwrite doesn't do a direct call to the next functions, but an indirect function call. And again, we cannot be sure which functions there are called there. And what we do here is we utilize, again, the compiler. The compiler knows which signatures are called, so what arguments the function get and what type they have. And by collecting all the information which we have again, we find that he has to call, in this case, standard outwrite. And in standard outwrite, we really have this syscall. So calling syscall 16 for an IO control and syscall 20 in the standard IO write is the write operation. All which is left then is to backpropagate this information up the call graph, and then we know what syscall's main uses. So to summarize, the key aspects that Sourcealyzer uses are that we use each tool for what it's best at. We use the compiler for extracting information he has access to, like the syscalls and function names and signatures. We embed all this stuff into the object file and then recombine it in the call graph into a call graph as part of the linker. Additionally, we use link time garbage collection to reduce the number of reachable functions, which helps with this indirect function call handling, and the function called signature heuristic, which I mentioned before, to figure out which functions are called indirectly. And the result of that is that no time-consuming whole program analysis is needed. So we can do this all much faster than our previous related work.
I think that's a very interesting idea, but the question that pretty much everyone is asking themselves is, does this really work, or is it just working for like a small example like Hello World?
So I was expecting that, of course. You are always quite skeptical with this stuff. So we tried it, of course, and as an example, we also tried it on FFmpeg. So you have all this video encoding stuff in there, you have parsers, a lot of potential spaces where vulnerabilities would be bad. And we compiled it with our Sourcealyzer tool and got a Sandbox binary. We have a quick video here which shows when we start this application, First, we look at what syscalls were found. In this case, 63 syscalls were extracted. And when we start the application with a debug flag, we again print what syscalls have been found, which were used for setting up the seccomp filters. And yeah, the application simply runs.
That's really nice result. So I have to say I used that on my simple application and it still works flawlessly. So it seems it perfectly sandboxed that, but I'm still not fully satisfied. So I have this old software lying around here that looks a bit shady. I'm not sure how secure it is. Maybe it even has backdoors or something. And I can't really tell because I don't have the source code. I only have this binary here. I would like to also sandbox that to make it a bit more secure at least. So I can't do that with your compiler, right? It requires source code as every compiler. So what do you do if I only have a binary?
Well, you obviously did not pay attention to what I said in the beginning. We also have this binary analysis tool that allows you to do exactly what you want here. So we have this binanalyzer. It extracts the system calls from existing binaries or libraries. And for that, it simply uses the capstone framework. So it disassembles the binary so that we get all the assembly instructions and uses, so we can find the system calls there. And then we use the Anger tool to build a call graph again and extract the system calls that are actually needed for the binary.
But Claudio, how does this work in detail? I mean, the syscalls, finding them sounds complicated.
It is a little bit complicated, so let me briefly walk you through this. So what we do is we rely on symbolic backwards execution. We look through the disassembled binary until we find a system call instruction. And typically the system call is executed is in the RAX register of the CPU. So you move at one point the requested number into that register, perform the system call instruction, and the system handles the rest for you. But we need to find this. So we look for the system call instruction, and when we find it, in this case, we simply don't know yet what is the value of RAX. So we keep the value symbolic, and we move back up a couple of instructions because at one point we are going to find this move instruction. But in the first two lines that we look at, we don't really find it. But at one point, we see that we have this MOV EBX to EAX register. Well, that still does not tell us what is the actual syscall that is executed, because suddenly EAX is EBX. So we need to keep the value further symbolic, but we now know that RAX is equal to RBX, which we don't know the value yet. So we continue our search. We don't learn anything else in the next line. But at one point, we'll see that we see a MOV instruction where the value 1 is moved into the BL register, so the lower part of the EBX register. So at this point, we can now infer that RAX is equals to RBX, which is equals to 1. So we know that the syscall that is being executed is syscall number 1. And
so help me out there. Do I have to do that manually?
No, the system, so our tool does all of that automatically for you. You just give it as an input your binary. We pass the binary so that we find all the dynamic dependencies of it, and it finds the system calls. We build the call graph with Anger, and using this tool we can then get the system call mapping where we know, for instance, that the puts function needs write v, that the fork function is going to need write v, sysclone, and sysfutex system calls. So all of that is done automatically for you. And we can also show you again using a video how this is done. For this, we use the application Redis, and we applied our binary analysis tool to it and executed the test suite of the application. And as we can see, not a single one of these test cases fails. So it seems like we find all the necessary system calls for our application.
I trusted you with that, so I applied that to my legacy application that I only have a binary. And surprisingly, that happened. It just crashed. It stopped working. So it doesn't work. Your binalizer thingy destroyed the application, so it's now completely broken. So why? What is happening here? You explained it so nicely. It made sense, but apparently it doesn't work.
Yeah, Michael, I think you found a corner case there which we simply cannot handle. So, I mean, seccomp filter, if you configure them statically, it's not possible to relax them anymore. I mean, that's a nice property for having for ensuring that an application doesn't gain additional privileges, but in this case, it's really not ideal. So what we actually have to do here is we need another approach. I mean, seccomp itself is nice if you know the static set, but we need additional capabilities. In particular, something like an S-trace approach, where we see all the syscalls and can decide during runtime if this belongs to the application or if it is a malicious syscall that we do not expect. We have a tool for that. It's called Finalizer. And what Finalizer does is it basically implements this S-trace approach. So we have a tracee, which is the application which we want to protect, and we spawn a second process, the tracer, which monitors the syscalls of our target application. What now happens when the application makes a syscall, the kernel automatically delegates this decision if the syscall is okay or not to our tracing application. Here we can log the syscall, we can theoretically decide if it's okay to do it or not, or simply take notes and log that the syscall took place and use that information for further refinement later on. Afterwards, the tracer, the monitoring component returns to the kernel and says, okay, the application is allowed to do this syscall, and then the kernel performs the actual operation. So when we look where we implemented that, we basically designed a new small utility library called libchestnut. This library is in charge of setting up seccomp filters on application start, and it also implements this finalizer approach which I discussed on the previous slide. The way it works is it registers a constructor basically, a constructor function like in a C++ program, but in this case in a C program, which is automatically called on program startup, and in this constructor we set up the seccomp filters. Additionally, Sourcealyzer, which we introduced before, automatically links to this library, so all you have to do there is to use the sandboxing flag and of the compiler, and you get the completely protected binary at the end.
So the question here is then, what about Binalizer? In Binalizer, we cannot simply link against it, right? So when we think back to the overview that I gave earlier, we had these two other tools there, Chestnut Patcher and Chestnut Generator. So they can be used for this. So Chestnut Patcher more or less uses the information that is provided, the number of system calls that are being executed or that need to be allowed, and directly patches the binary, includes them in a node section, and also links against libseccomp and libchestnut. So more or less you then have the same thing as you have with Sourcealyzer. The other approach would be to use Chestnut Generator. So instead of patching the binary, we create like a wrapper program that sets up all the filters using libseccomp and our libchestnut, and then launches the binary. And
okay.
Yeah.
That's pretty nice. So I can apply that to all my applications now, right?
Yes.
Okay, and yes, this time it really works. So I have to admit I'm a bit surprised by that, but it actually works. But I mean, still, you do a lot of stuff. You figure out syscalls, you have to do static analysis, some dynamic analysis, symbolic execution. That's a lot. Also adding all these filters. So isn't it going to be super slow?
Well, we obviously put some thought into that and performed some evaluation of all this. So we looked at the performance of our tools in extracting the system call information that we need. We also evaluated the functional correctness, so are tools actually still able to do what they want, what they need to do. And we also looked at the security, because in the end, that's what we are most interested in when we use SecComp. We want to improve the overall security of the system. And for that, we looked at client, server, and database applications. And in total, those were like 18 applications that we analyzed throughout these client, server, and database applications. And when we look at first the performance of our tools, we only provide the worst compile time overhead here. And we observed this for the Git application. And there we observed an overhead of 28%. 28% sounds quite high, but total that was like 19 seconds of overhead, and is actually quite fast when you compare it to concurrent work. Then for the worst binary extraction time, we observed as for FFmpeg, it's the largest application that we looked at. I think the binary was like 100 megabytes, and there it took 11 minutes to extract it using our binalizer.
All we discussed up until now is basically overhead, which we have at compile time or after, in a pre-processing step before we actually launch the application. But there is other overhead as well, which we should at least mention in terms of runtime, and especially. So Chestnut itself doesn't add anything in regards of overhead during execution, but we still use SecComp, and SecComp is not the fastest, if we are completely honest. But there is work ongoing to improve the situation, so it's not really in the scope of our work, but every improvement which goes into SecComp, which is part of the Linux kernel itself, automatically also improves our final solution, which is nice, I guess.
So that's great. So now let's take a closer look at the functional correctness. I mean, that's, after security, probably one of developers are most interested, because if your application doesn't work anymore, what's the security worth? So for that, we relied on the application's test suites for our checks. So we were not able to test pretty much all of them, but because they simply did not have test suites available. But we used those that had some available and let those run, and just checked, did these test suites complete successfully? Because if they did not, then we might have made a mistake. To substantiate that we are actually looking at the majority of the application, we looked at code coverage metrics for the better estimation of the correctness. And there we've seen that in regards to line coverage, we were close between 59 and 77%. And for function coverage, we were able to cover between 61 and 92% of the functions in these test suites. So this might also be a point that we need better test suites, but this is outside the scope of our work. What we also looked at, or what we've seen in these tests, is that we observed no crashes during these tests. So I think this is nice. It shows that at least for the main parts that are covered by the test suites, we are able to extract everything that is necessary. And additionally, what we also did is we performed a 6-month long-term study using Nginx, hosting one of our websites with it, and we observed no crashes over those 6 months.
Okay, so another important thing is, of course, the security. You already mentioned it. The whole point of this research is to improve security. And what we did to figure out how much we improved this, we looked at how many system calls have been blocked by our tools. So in particular, when you look at the socializer approach, we were able to block on average 87% of the syscalls which the Linux kernel provides, which is, of course, a really nice improvement already. Quite similarly, Binalizer also was able to block 83% of the syscalls on average, which drastically reduces the attack surface of the kernel. When we look at exec, which is one particular system call which is quite dangerous in terms of security, results were a little bit worse, but still we were able to block it in 9 out of our tested applications using the compiler-based approach, and even in 14 using Binalizer. Similarly, mprotect, which makes it possible to change the execution permissions of a page in memory. We looked at that in particular, and our sourcealizer tool blocked this system call in 61%.
All that is nice, but what we also did is we looked at mitigating real-world exploits. So we looked at the Metro database, looked for CVEs that explicitly mention that they exploit some kernel vulnerability that is triggered using a system call. And there we found 175 CVEs that did exactly that. We analyzed those CVEs. We found that some of them, there's an alternative system call that might also be able to exploit this vulnerability. So we simply replaced those with them and got a much larger data set there. So roughly 345 CVEs in that when it comes to that. And then we just took our applications, all these 18s that we had. We compared the system calls that the CVE relies on, or the exploit relies on, cross-referenced those with the system calls that are being allowed. And if we block the system call, then we consider that this CVE to be not exploitable via this application. And when we looked at the full CVE, so we can mitigate all of the variants of it, we were able to block 64 and 62% respectively using sourcealizer and binalizer. And for the subvariants, we were able to block even more, so 75 and 72%.
Okay, that's pretty impressive. But while you explained that, I wasn't listening too much, but I thought about some exploit technique that also injects syscalls in existing applications. So I was thinking about return-oriented programming, where I use existing code in an application to exploit a program. The idea is to simply, if you have control in the application because you exploited it, to jump to existing parts of the application, so-called gadgets, that do a part of the functionality and then return to the next gadget and so on, and you chain them together. So these gadgets could be as simple as getting some value from the stack into a register, or just executing a syscall. And with that, couldn't I still exploit your Sandbox application? I mean, if I look at that in detail, I'm suddenly using the stack pointer as the instruction pointer because I have the addresses there for all the gadgets I use. And then I'm returning into the application itself. I'm not loading any code. I'm not executing anything with the exec syscall. I'm not using mprotect for anything. So I'm just using existing code, jump to that, return again. The stack pointer acts as the instruction pointer to the next gadget. I execute that, return back, execute the next one. And with that, I can build my own code out of existing code that can do arbitrary syscalls.
But yeah, Michael, that's exactly the point. You can make arbitrary syscalls via something like return-oriented programming, but at least with the SecComp filtering, we can prevent it on the kernel side. So if you build a syscall that was not originally in the program and which our tools didn't find, the application simply is terminated as soon as you try it.
This demo does pretty much, we show here that it's actually sandboxed using our approach. It reads from some file, and then we start our attack, we crash the application, we find out, okay, we have some form of buffer overflow there. We perform our ROP attack that tries to spawn a shell. As we can see here with this pop-up, simply our system has detected this and asked us to clarify, hey, is this something that you actually want to do, executing this?
Okay, so I think it's really the best to just give it a try. All our tools are open source. You can find it on GitHub. You find it under the URL in the slides, and it's the best simply to try it out yourself. And also, when you're already looking up stuff, also check out our paper. It contains much more information on how the techniques actually work.
This really reduces this overhead, this manual analysis overhead, to actually sandbox an application and make it secure by having this automated process.
Yes, so that's very nice. Through this automated process, we were basically able to show that we can improve the overall system security using no manual labor pretty much at all. I mean, you need to modify some make files probably. We were also able to show the functional correctness using test suites, showing that our applications using the Chestnut Sandbox approach still work. And we were also able to show that Chestnut only has a small performance overhead in your everyday development cycle.
So that is something that should be developed further, which can help make systems a lot more secure without needing a lot of experts to do it. So thanks again, all of you, for being here, for paying attention.